games were horrible. Like the whole town of Northfield would show up and cheer for St. Olaf. Every single person who lived in Northfield. Yeah. Well, they thought we were really big jerks. I think a big part of it. So there were two things. Like one, St. Olaf was Lutheran, and Carleton wasn't anything, and Northfield was pretty Lutheran. Also, St. Olaf made a really strong effort to like accept Northfield high school kids, so like they felt like they were more part of the community. And then maybe the worst part was St. Olaf is off on its own. Carleton is like right in downtown Northfield, so like they had to deal with us. You know, they like, yeah, well, every Saturday at least, and I don't think that gives you the best impression. Uh, Often very bad. They won conference one of the years I was there, but often very bad, but not as bad as McAllister. Um, yeah. Okay, so we have exam 2 a week from today. So let me talk about that. Well, we have something even before that. So Friday is the lab exam. And that is going to ask questions that use the same line of reasoning as the questions that I've asked in the labs. It's not a group test, it's an individual test. And so you just need to go back over the labs, make sure that you understand the thought process for answering those questions. It's going to focus a lot on the kind of thinking about the directions of velocity and acceleration. So there will also be some questions about, remember the lab where we dropped something and got the little burn marks and you measured those and used those to estimate velocity and acceleration and stuff. There'll be some questions like that, so make sure you remember how to do that. Yep. No, all the equations will be on there. You just need to remember the process. So go back and study the labs. Know how to answer those questions. Anybody right now have any questions about the lab test? Also, apparently, you're not supposed to be walking around the school after. So, like a lab exam, when you're done, but we need to stay in our little area. I don't know. I think it just makes it like, I think it's just like, it's hard for Roger to know, like he wants to know where people are when he needs to get people, and he has multiple groups and whatever, so we'll just make it easier for him. Thank you. Okay, and then exam 2 is next Wednesday. That is the 28th. And I don't usually split up, like for topics on exams, I don't usually split up those sets of problems. But what we're working on right now is a really big set of problems. And so I'm going to I'm going to split this set up, and so the topics are going to be everything that we've done up through particle kinetics number 19. Okay, and what that is through pulling forces. So there's not going to be any friction forces and no spring forces. Yep. Yes, it's all cumulative. So what I would recommend doing with the old problems is just go back, look at the problems and ask yourself what the steps are to do it. If you know pretty clearly what the steps are to do it, then don't take the time to go through it again. But if you have trouble thinking of the approach, then that's a problem that you want to spend a little time on. Any questions about the test? That's next Wednesday, a week from today. And then the week after that, so like go back 2 days to Monday and then go forward 2 weeks. That's spring break. So the week of exam 2 is after that you get a little break from class and stuff.
So like the 5th or the 9th?
Yes. Now, anybody have any homework questions? Okay. Yes. In the order starting at 1 and counting up? Okay. Anybody? Yeah, please. Oh, okay. Well, so the first one, the question is, use Newton's second law to show that the acceleration of an object in free fall doesn't depend on its mass. Well, we know that we already established that the weight force of an object with mass m is mg down. Okay, so let's say we'll choose the y-axis pointing up. And in free fall, the only force acting is the weight. So Newton's second law says 0, negative mg, right? That's mass times 9.81 meters per second squared. So this is the weight force. And in free fall, that's the only force. So the sum of all the forces, which is this, is equal to the mass times the acceleration. So let's see what the acceleration is. So we'll say there's a x component of acceleration and a y component of acceleration. So we're going to calculate that. So we've always assumed we've known that, but now we're going to use what we know about the force to calculate that acceleration. The x equation says ax is equal to 0. I guess let me write that out. 0 is equal to max. So ax is equal to 0.
G is just a y. Right? It's really just.
Well, we're going to calculate it. So what we're starting with is we know the force that's applied because we talked about the force that's applied by gravity, and we're going to say what's the acceleration for this arbitrary object, and then we're going to just use those two equations, that one vector equation, to calculate what the components of acceleration are. I mean, it won't be a surprise because all through free fall kinematics, we were using the fact that the acceleration on any object in free fall is g pointing down. But that's what we're going to calculate here now, knowing the force. Okay. Okay, so we know the x component of the acceleration is 0. The y equation says negative mg is equal to positive may. And so the m's cancel, and you get that ay is equal to negative g. Okay, so the acceleration is 0, negative g. And so that acceleration doesn't depend on the mass. Okay. Okay, so what this says is the weight force, the force that gravity applies does depend on the mass. That's why things that have different masses weigh different amounts on a, show different numbers on a scale. But the acceleration in free fall does not depend on mass, which is why in that vacuum chamber, a feather and a bowling ball fall the same. Okay. And then number 2 is the second one you had an issue with? Okay. Number 2. So this thing slides in uniform circular motion across ice due to, so. Did you hear about that curler who got busted for steroids? It's very weird. And apparently his coach's argument was like he's a smart guy. If he wanted to dope, he definitely wouldn't do it in a way that you'd get caught. I think so, yeah. Okay, so this box has a mass of 2 kilograms. It's sliding. That's supposed to look sort of three-dimensional. I don't know if that really. Okay. No. That is 5. Okay, that looks the same. I'm not drawing it again. So it slides in uniform circular motion. We know that the length of this tether. Yep. And it makes 1 revolution every 1.5 seconds. So you could do that and calculate a speed. I think the way that I was going to do this, so let's draw it from above. Yeah, that's right. Omega, yep. Okay, so we're going to think about it here. And it doesn't matter which direction it's going. Let's say it's going this way. So this way. All right, so what direction does the velocity vector go? That's right. It's counterclockwise, so it's going up here. So there's the velocity. Is it speeding up or slowing down? No, so there's no parallel part. It is turning in a circle, so there has to be a centripetal part. Magnitude of that centripetal acceleration is omega squared r. So to get omega, we have 2 pi, 1 revolution is 2 pi radians, right? So it goes 2 pi radians every 1.5 seconds. So 4 pi over 3 radians per second. And so the centripetal acceleration magnitude is 16 pi squared over 9. Times 0.5. So 8/9 pi squared. And now in this coordinate system, the centripetal acceleration vector, that's pointing in the negative x direction. So for the x component, we have negative 8/9 pi squared. We have nothing in the y direction. And this is meters per second squared. And that's equal to the acceleration because we don't have any tangential acceleration. And now it asks for the net force. Newton's second law says the net force is equal to the mass times the acceleration vector, which is 2 kilograms times negative 8/9 pi squared 0. And so the net force is negative 16/9 pi squared for x, 0 for y, and that's in newtons. What's the direction of the net force to make this object move in this direction? Straight in towards the center of the circle, yep, in the negative x direction. Okay, so let's think of this implied part B. Oh, well, we haven't done cable stuff yet, but so what are the forces on this we know that the net force, so all the force vectors add up to this force pointing in towards the center. What are all the forces that act in the x direction? That's an acceleration. The forces are the things like contact forces, the weight. The weight isn't pointing in the x direction, right? It's like in the z direction. Same with the normal force, would be pointing out of the page. So the only thing that's producing a force in the x direction is the cable, the tether. And so what this says is that cable is applying a force with a magnitude of 16/9 pi squared in newtons. And if you have a cable that can't withstand that much force, it's going to break, you know. So what is that? It's like 160 tenths. So I don't know, 20 newtons or something. So if that tether is like a fishing line, and it's a fishing line that's not rated to withstand a force of 20 newtons, then that's going to break. Any other questions about that one? What were you asked to do up through 4? Yep. Okay.
The elevator one's pretty easy, right? But like 4 was weird. Pushing the little one.
Okay, so we did one pretty similar to the elevator one, right? Okay, so do 4. All right, so we have two 50-kilogram boxes that are positioned on rollers like little wheels. 75 Newton force is applied. And then there's a 75 Newton force applied to the left. And we want to calculate first the acceleration of the two carts. And then second, what force does the right box apply to the left box? So on the left box by the right box. So what's the tool we're going to use? What equation are we going to use to calculate the acceleration? Newton's second law, yep. So, and before you use Newton's second law, you have to draw a free body diagram. Before you draw the free body diagram, you have to choose what you're going to isolate. What are we going to isolate here? This is, yeah, just treat it all like one thing. To find the acceleration, that's almost always what you do. So isolate both of those as a single object. And the forces we have, there's a weight force. That's the mass of the thing we're isolating is 100 kilograms. So 100 times 9.81 is 981. And then there's a combined normal force acting up. We could split that up into a normal force for each one. I don't think the normal force is going to come into this in anything. So I'll just write this as there's a normal force N total that's pushing up. And then go around the boundary looking for other places where there's contact. There's contact at the other wheels, but we're lumping those all into one. So I'm going to skip those, keep going around. And the only other place that there's a force applied is on the left. There's that 75 Newton force. So what about the force that, like, the left part applies to the right and the right part applies to the left? Those show up here? No. Yeah, so we're only concerned about the forces that the surroundings apply to the boundary we drew. And so since those individual contact forces are inside the boundary, those don't show up. Okay. Newton's second law. You can see from this, since the x and the y are independent of each other, there's no reason to use the y equation because we weren't asked for anything about n total. So the x equation says 75 positive x direction is equal to mass of the combined system times the acceleration in the x direction. I'll just call that a because this wouldn't have any acceleration up or down. And so the acceleration is 75 over 100 or 75 meters per second squared. That's in the positive x direction. And so the total acceleration vector is 0.75 in the x direction, 0 in the y direction.
So it's being pushed with 75.
No, that's the acceleration. Oh, 70, yes, 75. Yes, that's right.
And that equals 100 kilograms.
Yeah, that's Newton's second law. It says add up all the forces acting in the x direction. Those have to add up to the mass times the acceleration in the x direction. And we don't care about anything happening in the y direction. So, and we know that there's no acceleration in the y direction because it's just sliding along a surface. It doesn't even have to be constant. It could be jerking around back and forth like this. It still isn't going to be hopping up into the air, you know. And so we know that the y component of the acceleration is 0 because its x, because its y position is just going to stay constant, and so its y velocity has to be 0. So its y acceleration has to be 0 the whole time.
Okay, so for the next part, it said to multiply 50 by 0.75. Why do we multiply this?
Okay, so now what we're going to do, we're just going to use Newton's second law again, but we're going to isolate something different. So for part B, we're going to do a free body diagram. We want to know the force vector applied to the left box by the right box. So I'm going to draw a free body diagram of, so we want to find a force that's on the left box. So I'm going to do a free body diagram of the left box. And what forces are acting? There's a weight. Now, since we're only isolating one of these, that force is 50 times 9.81. So 490.5. Then there's a normal force up. The ground's pushing up, so I'll call that N50. That's not the same as the N total before. And now keep going around. Do the surroundings make contact with this object on the right side? Yes, that's the pushing contact applied by the other box. So there's a force this way. It's pushing, so it's toward the chosen body. And I don't know, I'll call that R. That's the force vector we're trying to find. Then keep going around, and there's the 75 Newton force over there. Any questions about the free body diagram? So then Newton's second law, I'll just use the X equation again. It says positive 75 minus R is equal to the mass of what we're isolating this time times the X acceleration of what we're isolating, and we already know what that is. We solved for that in part A. That's Newton's second law. Add up all the forces. They have to be equal to the mass times the acceleration. So every problem in this set of problems is going to use Newton's second law, probably even every part of every problem. And now we just solve for R. So R is equal to, I think that must be 37.5, yeah. And so now if you want the force vector that's applied, we want to represent that force vector. All right, that is like the force on the left by the right. That has a magnitude of 37.5. It acts in the direction of that arrow, which is the negative x direction. So this is negative 37.50. Any questions about that? And so again, in an engineering type application, once you calculate what that contact force is, you know something about what kind of materials you can build this out of to keep it from breaking. That's how you use this information. Any other questions about that one? Okay. Okay, so we're going through this list of different force types. There's the force applied by gravity. That's the weight. There's the force applied by pushing contact. There's the force applied by pulling. That's usually involving cables, or if it doesn't involve cables, you can reimagine the problem involving cables. Then there's friction. And then there's spring forces. We've done this one and this one. And so now we're going on to pulling forces. And these three are the only ones that we're going to do for exam 2. These last two will be after exam 2. Okay, so pulling. And usually we'll think of this in terms of cables. In everyday speech, a cable is like a sort of a braided collection of steel fibers. We're being a lot more general in this when I say cables. We're talking about string or rope or leather strap. a cable is anything that you can apply a force one way, but if you try to push with it, it'll collapse. Okay, so a cable is something that can only pull, it can't push. Okay.
So that wouldn't be like a rubber band because that stretches and therefore.
Right, a rubber band
That would be
would be more like a spring. Yep. The rubber bands, we're going to depend on a linearity with the spring. We'll see, and rubber bands are nonlinear, but otherwise they work the same. Okay, so the kind of thing we're going to do is, say you have two carts that are connected by a cable now. Say that's cart 1 and that's cart 2. What's the force applied to cart 1 by the cable? And all you need to know about the direction of a pulling force ever is that the direction is parallel to the cable and pushing contact was toward the chosen body, pulling contact is away from the chosen body. I think a nice way to think about it, especially when the problems get sort of complicated, is when you choose the body to isolate, include a little tiny bit of the cable in what you isolate. I'll call it a little stump. If you include a little stump of the cable, force is just straight out of the stump. So, for example, if this is a free body diagram of cart 1, cart on the left, you have the weight force, you have the normal force, and then the cable force just goes right out of that little stump of cable. I'll call that T for tension. It makes sense, the directions of pushing and pulling forces, if you think about like what. Yeah. So think about applying, so my shirt's like hanging here like this. So think about like which direction does my shirt go if something pushes on me? It goes, say, so I'm the chosen body. Push, if you push on me, pushes my shirt toward the body, If you pull on me, it pulls the shirt away from the chosen body. And that's the direction the forces are applied. Okay. Okay, so let me do an example problem. So let's say, what are the masses? let's say we have a 5 kilogram cart connected by a cable to a 2 kilogram cart. And then a 20 Newton force is applied there. And we want to know the acceleration of the system. Yeah. And second, what's the force applied to a 5 kilogram cart by the cable? And then let's do a third one, calculate the force applied to the 2 kilogram cart by the cable. Okay, so the first thing we want to calculate is the acceleration. What do we want to isolate to calculate the acceleration? Both, yep, almost always. Yeah, or just, yeah, I'm going to draw it like, yeah, so I'm going to draw it like this. You don't have to spend a lot of effort on the getting the outline just right, but just so you can tell clearly what I'm drawing. Yep. That's right. It doesn't matter at all, you know, and if you think about the fact, like, there's really no objects. Like, we think of it that way. Everything's just a collection of billions of atoms and stuff, you know. So whenever you draw the boundary is arbitrary, as long as you can make a closed outline around it. In this class, we're not going to do that, I don't think. But in engineering applications, you do that all the time, and that's how you figure out where something is likely to break, where you're concerned about something breaking. Okay, so isolate the whole thing. So we have the 20 Newton force over here. We have the weight force of the whole thing, which is 7 times 9.81, so 68.86. 68.67. And then we have the normal force. I'm going to lump that all together again. Just call that N total. Is there anywhere else where the surroundings make contact with the boundary there? Nope. That cable's included in our chosen body, so we're not going to see the force that that cable applies to different things right now. Okay, so Newton's second law. Just doing the x equation. What are the forces in the x direction? Yep, that's the only one. And that's in the positive x direction. So positive 20 is equal to the mass of the chosen object, 7 kilograms, times the acceleration. There's not going to be any acceleration up or down. This is just moving along the flat surface. So this is going to be the only part of the acceleration. And so A is equal to 27th. Yeah. I don't know what 1/7 is. 2.857. meters per second squared. And so the acceleration vector is 2.857 for x and 0 for y. Yeah, we will do ones where it's rolling down a hill. But the way we're going to do that is instead of having to worry about the directions of all these different things, we're just going to tilt the coordinate system. And it's going to keep a lot of that stuff simple. Yeah. Didn't think of that myself. This is question 1. We figured out the acceleration vector of the whole system. Okay, so now for part B, we're trying to figure out the force vector applied to the 5 kilogram by the cable. We're trying to figure out the force applied to the left cart by the cable. So I'm going to isolate the left cart, draw a free body diagram of the left. I'll call it the 5. So what forces are acting? There's a weight force. 5 times 9.81 is 49.05. There's a normal force, the ground pushing up. So that's, I'll call that N5. Yeah, let's include this. The cable. And so the force vector applied by the cable comes right out of the stump. And give it a variable name. I'm just going to call it T. People usually use T for these. And then is there anywhere else that the surroundings contact that boundary? Nope, that's it. So Newton's second law again. And we'll just use the x equation again. So we have this T acting in the positive x direction. And that's equal to the mass times the x component of the acceleration, 2.857. So T is equal to 14.285. And then if you want the force vector, we know it's pointing in the positive x direction from looking at the free body diagram. So the force on the 5 by the cable is positive 14.2850. Yeah, so let's just go through all the steps. Especially at the beginning, you want to be careful about all these steps. Make sure you're thinking right about the vector directions and what forces are applied and stuff like that. Okay, so Newton's second law now for the, well, free body diagram for the 2 kilogram. There's a weight force. 2 times 9.81 is 19.62. Yeah. It's going to be the cable over here, so I'll include the stump this way. There's a force vector from the ground. I'll call that N2. There's the force this way of 20. And then this way, there's this cable force. I'll call it T2. Okay. Well, what we're going to see is that force T2 is going to have, it's in a different direction as the force that the cable is applying to 5, but it's going to be the same magnitude, and that always has to be true for any cable. The force it applies to any object has to be the same. Okay. So Newton's second law, x component says this T2 is in the negative x direction. We have negative T2. The 20 is in the positive x direction, so plus 20 is equal to the mass, 2, times the acceleration, 2.857. And you get T2 is equal to 14.285. You might get 0.286, but that's just round out there. No, it's going to be, so the reason that we have it negative in Newton's second law is because it's pointing in the negative x direction. And so then you just do the algebra for it, and you get a positive number. And now if you want to calculate the force vector on the 2 by the cable, you take this magnitude, the 14.285, and we know it's acting in the negative x direction. So this is negative 14.285. So what we saw, notice, this is an important fact about cables. The force a cable applies to anything along its length because that 20 wasn't applied to the boundary when we isolated. So when first we isolated both of them, and then we isolated this one, and that 20 isn't applied to the boundary of this one. It's applied to something else. So it just doesn't show up. It does affect these other forces, obviously. Like indirectly, it's definitely determining what's happening. But all we have to do is draw the boundary here and then put in the forces that are applied to that boundary.
So the forces are T equal mass times acceleration.
For the first one, yeah.
And then why does it squared?
No, that's just T2. I'm just calling it a different variable name. But what we saw was T and T2 have the same magnitude, and that always has to be the case. So the force a cable applies to anything along its length has the same magnitude and that magnitude is called the tension.
And what number did you multiply?
That was the acceleration that we got from part A.
The 27.
27?
27.
Oh, yes. Any other questions about that? Okay, let's take a break and start again at like 9 o'clock. So now the next thing that we're going to do with cables is cables can cross over pulleys. And pulleys are really just a stand-in for any kind of frictionless contact, but yes, that's what it does. So, so now we're going to include pulleys. We're going to assume that these pulleys are massless and frictionless. And all a pulley does is change the direction of the force the cable applies to things. So all it does is change the direction of the force the cable applies to the objects it contacts. I remember when I first took physics. What? Question? It sounded so funny. When I first heard about pulleys in physics, I was sort of confused about this because I remembered being like younger and being told about this thing, pulley advantage, and being told that pulleys are like one of the 7 simple machines or whatever. And no thanks. So, and you can use pulleys in a way that you can lift something that has a weight of 100 pounds by applying a 50-pound force or something. You can use pulleys that way, but it's not the pulley itself that does it. It's a sort of a smart configuration of pulleys that lets you take advantage of that. A single pulley by itself, all it does is change the direction of the force. And so I'll do an example later where we'll see how pulley advantage works. But for now, just keep this in mind. It doesn't change that force at all. So let me start with the simplest example, and then I'll do another one. So first, let's just think of a pulley connected to the ceiling. So you're holding up a mass of 10 kilograms. And you're applying a force F. Actually, change that. Let's give it an actual force. Let's give it 150 newtons. The acceleration of the box. Okay, so I'm going to isolate the box. The 10 kilogram mass. I'm going to include a stump of the cable at the top. And the forces acting on that box are the weight acting down, so that's 10 times 9.81, 98.1 newtons. And then there's the cable force at the stump. We know it's going this direction. What's the magnitude of that force? 150, because all that pulley did was change the direction of that force. It didn't change anything about the magnitude, so we just have that 150 acting up. And so now Newton's second law, if we only look at the y equation because nothing's happening in the x direction, we have positive 150, because that's in the positive y direction, minus 98.1, because that's in the negative y direction, is equal to 10 times the acceleration. And so 51.9 is equal to 10a. So A is equal to 5.19 meters per second squared. So then what would that be as an acceleration vector? Yeah, perfect. 0x 5.19 in the positive y. Any questions about how I got that acceleration? So we knew that nothing was happening in the x direction, so we knew the x component was going to be 0. We used the signs of the y components to come up with a number for the y component of acceleration. Since that was positive, we know the y component's positive. That's the weight. The thing has a mass of 10 kilograms, so 10 times 9.81.
Oh, 10 times the acceleration down.
So on the left side are the forces. This is the force applied by the cable. This is the force applied by gravity. The cable's pulling up out of the stump. Gravity's pulling down. And then the right side is the mass times the acceleration, the y component of the acceleration. And so that's what this is. And then we just algebraically solve for A. Okay, so now let's think about what if instead of a known force, so we have a similar setup, a pulley connected to the ceiling. And let's say we still have a 10 kilogram box on this side. But now on the other side, we have a 5 kilogram box. And say we want to calculate the acceleration of the 5 kilogram box. Well, now whichever one of these two boxes we isolate, we have a cable tension acting, and we don't know what that is yet. Okay. So we're going to have to solve this as a system of equations. Whereas last time we right away could just replace the force of the cable with the force, that was applied to the other end of the cable.
So depending on the tension of the cable, it'll either pull the 5 kilogram weight up, or it'll come to like equilibrium.
Yeah, and if everything's frictionless, you can tell just intuitively that the 10 kilograms can accelerate down, the 5 kilograms can accelerate up. So one other thing that we're going to have to get to is the fact that we're assuming that this cable doesn't stretch means that there's a relationship between those two accelerations. So, like, if we pull the 10 kilogram box down 1 inch, where does this one go? Up 1 inch, right? There's that one-to-one relationship. That holds with positions, with displacements. And because of that, if you take the time derivatives, it also holds with velocities, and it also holds with accelerations. So if this one has a downward acceleration of A, this one has an upward acceleration of A. Okay? So let's first isolate the 5 kilogram box. There's the stump. The weight acts down 5 times 9.81, so 49.05. And then there's a force pulling up that I'll call T, the cable force. And then Newton's second law. The Y component says we have positive T, negative 49.05 is equal to 5 times, let's just call this for now, let's call this A5, okay? So that's the acceleration of the 5 kilogram box. So this gives us our first equation. I'll write it as T minus 5A5 is equal to 49.05. Can we solve that? No, two equations. One equation, I mean, two variables, so we can't solve it. Now what do we do? Isolate the box, use Newton's second law, and we'll get a second equation. Okay, so free body diagram of the 10 kilogram. There's a downward force of 10 times 9.81, 98.1. There's the cable force out of the stump. What's the magnitude of that cable force? T. We don't know what it is yet, but we know it's the same T as the other one. And then the second law, the Y component says positive T minus 98.1 is equal to the mass times the acceleration of the 10. And I'll rewrite this one, and it says T minus 10A10 is equal to 98.1. Can we solve that system? Well, not yet, because I have separate A5 and A10. But now we're going to use the fact that we have a known relationship between those two. So we know that A5, and I'll just call that A. Well, all that a cable can do, all that a pulling force can do is apply a force parallel to the cable away from the chosen body. And so that's what the rules say it has to be. But they have to be pulling up because, well, imagine two things that have the same mass and they're not accelerating at all, you know. If the cable wasn't there, they would fall to the ground, you know. So the cable has to be counteracting gravity in both cases. Okay, so we'll say A5, we'll call it A. is equal to negative A10. And I'll rewrite these equations. So we have, the first equation says T minus 5A is equal to 49.05. The second equation says T and I'm going to substitute in, what this says is A10 is equal to negative A. So I'll substitute that in. T plus 10A is equal to 98.1. Yeah, that's what we're trying to find. So, but you could do it either way. And in the end, you just have to, you'd have a negative answer and blah, 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 but you'd get the same thing if you thought it all through. Okay, so there's our system of equations, two equations for two variables. And the answer is A equals 3.27 meters per second squared. That's in the positive y direction. So what that says is the 5 kilogram box accelerates at 3.27 meters per second squared. So the 10 kilogram box accelerates down at 3.27. Yep.
Oh, it doesn't matter. Is that like 49 over 50?
I guess 49. Yeah, that's right. 49 over 15. That's right. Yeah, right. Any other questions about that one? Oh, yes. Yeah. So we made this, we said that A5 was equal to A. Okay. And then we used the fact that, what I was saying before, if you pull one of them down an inch, the other one has to go up an inch. And since there's that 1 to negative 1 relationship between positions, you can take time derivatives, and that ratio of 1 to negative 1 carries through the velocity and the acceleration. So the acceleration of one is the opposite of the acceleration of the other. It has to be that way. And you can always think that through in any problem by thinking, what would happen if I pulled this one down an inch or let this one move up an inch? So that's where that comes from. We said A5 is equal to A. We know A10 is the opposite of that, so it's equal to negative A. And then that was the variable I solved for. Okay, what about the tension? So anybody have any guesses about what the tension would be? We have these two things hanging. So you might have like intuition like that. You might think that it's going to be the weight of one of them or the weight of the other one or the weight of both of them combined. But it's not. It's going to be somewhere in the middle. And that has to do with the fact that you're dealing with the acceleration in addition to just the weights of those two things. Yep. Right. Yep. Well, let's calculate it because we have this system of two equations for two variables. We got the one here. To get that, we have to solve the other one anyways. And T is equal to 65.4 newtons. The weight of 5 kilogram is 49.05. The weight of the 10 is 98.1. So somewhere in between the two weights. So any intuition you have about from looking at the problem, like, oh, the weight's just going to be this or just going to be this, don't trust that intuition. It's going to be it's something you have to calculate. Okay, that tension, and the reason that it's something you have to calculate is because the acceleration in Newton's second law messes everything up. If they were at rest, if they weren't accelerating, then the tension would just be the weight. Okay, let's do another one. No, that doesn't work either. The average is like 75 or something. Oh, how did I get 65.4? I just solved the same system. We have two variables. Right. Okay, so let's say now we have a rolling part with a mass of 5 kilograms on this surface, and a pulley at the corner connects that to a hanging mass. Let's say the hanging mass is 2 kilograms. What's the acceleration of the 5 kilogram mass? Yeah. All of these you could do as 2D, and then what you would just see, like if I had started the last problem as two-dimensional Newton's second law, we would have just seen that one of the equations was 0 equals 0, and we would have thrown it away then. You can think about all of these as two-dimensional problems, but I've only been writing down the equation that's useful. Mm-hmm. Yeah, we can do it. So what we'll end up using is the X equation for the 5 kilogram and the Y equation for the 2 kilogram. Okay, so free body diagram of the 5 kilogram. There's the weight, 49.05. There's a normal force, I'll call it N5, pushing from the ground. And then there's the tension T coming out of the stump. Newton's second law. I'm going to write this. Yes, question? Oh, just stretching. I'm going to write this as a full two-dimensional equation. So that table force, question? Nope, it's not going to be. And the reason is that the acceleration messes it up. It's getting pulled toward the edge. Yeah. Nope. Because the inertia of the 5 kilogram cart is fighting against that thing being in free fall. Yeah, but we're just gonna do it in a really systematic way, write down the forces, use Newton's second law, and eventually come up with a system of equations we can solve. Okay, so that cable force is in the positive x direction. So that's T0. Yeah, we're gonna have to wait till Wednesday, I think, Friday, Monday. Yeah. Then the weight force is 0, negative 49.05. Then the normal force is 0, positive N5. Those are all the forces. And then those are equal to the mass, 5, times the acceleration. What do we know about the acceleration of the 5 kilogram? Its direction. What's its direction? Yeah, and we don't even have to know whether it's accelerating to the left or the right. Just knowing that it's accelerating horizontally is enough. So I'm just gonna, all I need to know is that it's gonna have an x component and no y component. And I'm just gonna call, yeah, well, there's no, right, having a vertical acceleration would mean like sinking into the surface or jumping off the surface. And that's not happening. It's just rolling along. T is a force. Everything on the left side is a force. A5 is the acceleration. And it's only happening along the x-axis. Okay, so from this you can see N5 is equal to 49.05. The x equation says T minus 5A5 is equal to 0. Y equation says N5 is equal to 49.05. And now we'll go to the hanging mass. So free body diagram of the 2 kilogram. Yep. Yeah, 19.62. Yep, perfect. And Newton's second law says 0t plus 0, negative 19.62 is equal to 2 times, now which way is this going to accelerate, along x or y? Yep, so 0, a2. Any equation that says 0 equals 0 obviously doesn't help, so the only useful one is the y equation that says t minus 2a2 is equal to 19.62. Yep. So now we have these two equations. And now I'll say A is equal to A5. And so therefore A2 has to be negative A. Because if you move you move this box in the negative y direction. This one moves in the positive x direction. So that's the relationship that those acceleration vectors have to have. So now we can rewrite this system of equations. The first one says t minus 5a is equal to 0. The second one says t plus 2a is equal to 19.62. System of equations. And you get that a is equal to 2.803. And t is 5 times that. Thanks. So t is 14.04. 0.014 newtons. Any questions about that? Yes.
So, like, for all these types of problems, like a sub 5 and a sub 2, like, it's not gonna matter, right?
Well, so if you can jump right to just doing it all in terms of one variable, feel free to do that. But if you can't, then call those accelerations different variables and later go back and think about the relationship between them. So that's the way I was sort of doing it. Okay, so remember, Friday is the lab test, so look back over the labs, make sure you're ready to do those problems.